what is light?
If you go to Harvard University, from where I got recognition, you can go to one of the physics classrooms and you will hear a voice coming out from all directions. In the beginning, God said the four-dimensional divergence of an anti-symmetric second rank equals 0, and there was light.
Wow.
Soborno Isaac Bari, known as God of Mathematics.
So Dr. Kabat, this is the story for light, and 4 people wrote this story.
Who were the 4 people?
Albert Einstein, Isaac Newton, and Niels Bohr.
Okay, very good. So what did Isaac Newton do?
Just like everything else in modern science, our understanding of light comes from Sir Isaac Newton. He was the first one to understand the rainbow. He refracted white light using a prism and separated it into its component colors: red, orange, yellow, green, blue, and violet.
Wow. And what is the difference between the marker you are holding and the sun?
Marker reflects light, sun emits light. The light that hit my eyes actually originated 93 million miles away. And it traveled that 93 million miles before bouncing off the marker and bouncing into my eyes.
Wow. But what exactly is emitted from the sun? Is it a particle like an atom, or is it a wave like a wave on the surface of a pond?
Newton used light as a particle, so he could explain refraction. Refraction is when something bends, put something from air into water.
And what did Max Planck do?
He discovered E equals hf.
Oh,
God, it literally took him 5 hours to write H because he didn't want to violate Newton.
I see. Okay. And what did Niels Bohr do?
He was a Danish physicist who contributed to the Bohr model. That's how he won the Nobel Prize.
Good for him. And how about Albert Einstein? What did Einstein do?
He put a barrier in the behavior of light. Light can only go as fast as 3 times 10 raised to the power of 8.
Wow. Okay.
He also stated that light has a mass, and therefore light must behave like a particle even though it is a wave.
Wow, that's a very confusing thing. So let's start our conversation with hydrogen. How does that sound?
Sounds good.
What is the Rydberg formula for hydrogen?
1 over lambda is equal to the Rydberg constant, parentheses, 1 over n initial squared minus 1 over n final squared. N being the constant that represents what state it is on.
Oh, wow. Okay.
This model contributes to the Bohr model.
I see. Okay, that's great. And can you tell me why the colors separate when they, say, go through a prism?
One color bends more than the other. For example, take Newton. He refracted white light using a prism, right?
Mm-hmm.
White light went into the prism. It got separated into those 6 colors that we see in the rainbow because one color bent more than the other. In this situation, the violet bent more than the yellow and red.
I see. Okay. And how about energy levels? Can you tell me about energy levels? Is the energy of an electron quantized?
Yes, because the electrons can't have to be in the loud states. They can't be in 1.86 or an 2.43.
I see. That those aren't allowed. those aren't allowed. It has to be in an allowed state.
Yeah.
Okay. Can you?
It can't be continuous. The energy is discrete.
I see. Okay. Can you draw the energy levels of hydrogen? Maybe from 1 to 5.
Okay. Let's see. So, don't confuse the Bohr model of an atom with a nucleus.
Okay, I'll try not to.
This is the state 1. This is state 2. This is state 3. This is state 4. And this is state 5.
Oh, nice atom. Could you tell me, could you calculate the energy of some of these levels?
So let's see. Let's draw a Bohr model. So this is E1. So this is N1. This is N2. And this is N3. So you might be asking, how do we find E1, E2, or E3?
That's exactly what I'm asking.
First, okay, so E1 is negative 2.17 times 10 raised to the negative 18. This has something to do with energy levels / the Bohr models.
Uh-huh.
1 electron volt, though, is 1.6 times 10 raised to the negative 19 joules.
Uh-huh.
We want to convert E1 into electron volts.
Okay, let's do that.
So, E1, negative 2.17 times 10 raised to negative 18 joules. This is technically on the top. So, we want this to be multiplied by a fraction. 1 eV, since we want to convert this to electron volts, must be on the top, over 1.6 times 10 raised to the negative 19 joule is on the bottom. We can cancel out the joules, so the only unit remaining will be the electron volts.
Oh, good, that's what we wanted.
So negative 2.17 over 1.6 times 10 raised to the first, since 19 minus 18 is 1, so basically 10 electron volts. So negative 2.17 over 1.6 is negative 1.3625. And if you multiply that by 10, you will get negative 13.
Okay.
So now, since we found E1, you might be thinking, now we can find E2 using this method, but we can't.
Oh.
Let's use this equation for any number. So E of any given number is equal to the value of E1 in electron volts over, and that his certain given number squared.
I see, okay. Oh, good. So can you use that to get E2?
Yes. So if we plug in n is 2, then we would get this. 625 or 4. So negative 3.40625.
I see, so that's how you get E2?
Mm-hmm.
Very good. How about E3?
So let's put the value of E2 here.
Good idea.
You might notice that E1 and E2 both end with a 625.
Huh, that's curious. I never noticed that before.
Now let's find E3. Besides, this time it won't end with 625.
Well, okay. Let's see.
Let's plug it in. E3 is negative 13.625 over 3 squared in 9. So that is equal to negative 1.513, a couple of 8, 9.
Oh, you're right. It doesn't end in 625.
Although E4 does. E4, the spoiler warning, is negative 8.8565, 0.8515, mistake there, 625.
Oh, let's see. Okay. It's curious.
No more states end up with 625 though. It's kind of weird.
It is kind of weird. I have another question for you. How much energy does an electron need to jump from the ground state to E3?
Okay. Let's calculate. So that would be E1 minus E3. You might be thinking, how are we going to subtract those? Because this thing is both of these are negative.
They are, that's right.
Minus and minus make plus. So negative 13.625 minus plus. So plus 1.513, a couple of 8, 9. I don't have a calculator here, so.
Okay, well that's pretty good. I could put that in my calculator to work that out. So would you like to talk about the photoelectric effect?
Okay.
So tell me, in the photoelectric effect, where do electrons get their energy from?
Photons. So imagine you have this piece of metal and you have electrons there. So those electrons are bound to the nucleuses in the atom. If a photon with the right type of light and the right type of frequency hits it, then photons basically come from light. So you could try shining a flashlight at it. So if a photon with a right type of light and the right type of frequency hits the electron, it can knock that electron loose.
Really? Okay. Wow.
The free electron is called the photoelectron.
I see. Okay.
It has a mass and even velocity, so we can calculate the kinetic energy of this photoelectron.
Really? So just for example, if a photon with a wavelength of 525 nanometers hit a metallic cesium atom, could you figure out the velocity of the photoelectron?
Ke is half mv squared. This one applies to physics. Ke is also the energy of a photon minus the work function, which we're going to say not. There are about 91 metals in the periodic table, each with their own work function.
Oh, okay. Do you know what the work function is for metallic cesium? I think work function is maybe it's 3.43 times 10 to the minus 19 joules.
So, wait. First, let's find the energy of the photon. That will be necessary for finding the kinetic energy, and we want to find the velocity, right?
Yes.
So, half of Ke also has an equation with the photon. So that we can use later is E photon minus E work function is equal to half mv squared.
Oh, very good.
So for now, let's focus on the energy of the photon. E photon is hc over the wavelength.
Uh-huh.
So that's equal to Planck's constant is 6.626 times 10 raised to negative 34 times the speed of light.
Uh-huh.
If you find it in decimality, you would actually get this value.
Uh-huh. It's a good estimate.
This divided by the wavelength. 525 nano stands for 10 raised to the negative 9.
Uh-huh.
So 525 times 10 raised to negative 9 meters.
Okay, very good.
I think nano stands for negative 9 from the late Latin.
Oh, maybe so. Ah, good. So that will give you the energy of the photon?
Yep. So 6.626 times 2.998.
So that's the energy of the photon?
Not yet. Don't forget about the bottom of the fraction.
Uh-huh.
So 19.864748. Divide that by 525 and you get 0.0378. This calculator is really good.
Oh, no, it's, you're doing a good job with it.
Times 10 raised to the negative 26 plus 9 is negative 17. So 3.78376 times 10 raised to negative 19. That is the value of the energy of the photon.
I see. Okay, very good.
Use E photon minus E, the work function, let's say E naught, is equal to half mv squared.
Uh-huh.
So we can plug in our values. So 10 raised to negative 19 minus 3.43 times 10 raised to negative 19 equals half mv squared. You can always have a common denominator, like in division. So let's work this out. 3.78 37615 minus 3.43 is 0.353615. 0.353615 times 10 raised to negative 19. That's the common denominator, as in division, equals half mv squared. So 3.537615 times 10 raised to the negative 20, right? Equals half mv squared.
Very good.
Now we'll multiply both sides by 2. So 3.537615 multiply that by 2 is 7.07523. So 7.07523. And so yeah, times 10 raised to the negative 20 equals equals mv squared.
Very good.
Because 0.5, I'm pretty sure is the reciprocal is a 0.5, which is half.
Uh-huh. I think you're right about that.
So
Now what you gonna do?
We divide both sides by the mass of an electron,
Very good.
so we can isolate V. So 7.07523 divided by 9.11 equal times 10 raised to negative 20 plus 31 is 11 equals to V squared.
Good.
So 7.07523 divided by 9.11 is equal to 0.776644346. That's a long list of decimals.
It is.
And you need to look at your calculator for some sure amount of time. So 0.776644346 times 10 raised to the 11.
Mm-hmm.
So 7.7664446 times 10 raised to the 10.
Uh-huh.
Now we're supposed to take the square root of this. That will cancel out the square.
Oh, good.
So 7, wait. I see you, Mickey square root button
Did you find it?
here.
There it is.
So the square root of 7.766. Sorry, I was looking at the wrong thing. I was looking at this. At least I didn't make a mistake. So 7.766444346. Make the square root of that? 2.78. So good. 2.786833949. Long list of decimals, eh?
Yeah.
So, two point 78668333949 times 10 raised to the 5th.
Oh, good. So that's...
So it's followed by 5 zeros, right? 1, 2, 3, 4, 5. 2, 7, 8, 6, 8, 3, 3. So it's 2.7 times 10 raised to the 5. Yeah.
Good. Wow, that's a fast electron. Could you tell me the energy of the light that's emitted if an electron jumps from n equals 3 to n equals 2?
First, every electron that lands from whatever certain state that is above from 2 all the way down to state 2 is called the Balmer, is in the Balmer series.
I see. Uh-huh.
The Balmer series is visible light. I don't know what Passon bracket or P-fund are, but all I know is that Balmer series are visible light, and the Lemon series, which is landing at state 1, is ultraviolet.
I see. Okay.
So Lemon series, the shorthand for ultraviolet is UV.
Uh-huh. Okay.
So this is in the Balmer series.
Oh, good. Because that way you'll be able to see it. That's good.
Rydberg's constant, Planck's constant times the speed of light, parentheses, 1 over n initial squared. 1 minus n initial squared, right? Minus 1 over n final squared.
Uh-huh.
So let's plug all of those things in. The Rydberg constant, 1.0974 times 10 raised to the 7th times the Planck constant, 6.626 times 10 raised to the negative 34 times the speed of light.
Mm-hmm.
the 8. So, what times 1 over an initial squared. So, 3 squared is 9 minus 1 over n 4 squared. So, 2 squared is 4. We need a negative answer here. That means it's going down.
Uh-huh.
If there's a positive answer here, I'm pretty sure it goes up, but Dad never told me.
I think you're right about that. If it's positive, it would be going up.
Okay. There's a lot of black ink on my hand right now.
Uh-huh. Is that okay?
So let's multiply all these things together. 1.0974 times 6.626 times 2.998. Boy, this calculator is good. 21.79957446. Lots of lists of decimals.
Mm-hmm.
21.79957446 times 10 raised to the negative 34 plus 15 and negative 19. 1 over 9 minus 1 over 4. So negative 0.111 repeating minus 0.25.
Mm-hmm.
Here, 1 divided by 9. See, there's 1 repeating.
Uh-huh.
Our answer minus 0.25 is, it's going on and on forever.
I see. Uh-huh.
All I know is that at the end there is a 9. So negative 0.13, a cup, oh, wait. 21.79957446 times our answer. So negative 0.13, repeating 8, 9. So our answer times 21.79957446. Negative 3.027718675. We're getting closer.
That's good.
So negative 3.027718675 times 10 raised to negative 19. This negative means it's going down. So it's not really very special. So once we find the frequency, we'll be able to drop that value.
Okay. All right. Very good. So can you tell me what the frequency is for that photon?
Okay. So I think it should be leading up to black holes at this point.
Oh, all right. We're going to get to black holes. Oh, very good. Okay.
So negative. Okay. So frequency is. Oh, great! I forgot it. I wish wormholes were real. Oh, great.
Me too. But let's see. So is there a formula for the frequency?
I forgot.
Maybe is
It's in my living room, but I can't go through a wormhole.
Okay. Well, is the energy maybe equal to?
Wait. Energy is HF, right?
Very good. That's the formula.
So F is H over E, right? No, it's E over H.
There we
It's
go.
swapped. So the energy of the photon, so delta E divided by the Planck constant,
Uh-huh.
which I think Planck wrote like a raw noodle
Is that right?
or something. So that's equal to -3. Oh wait, we can drop the negative value now. Sorry. So 3.0277186675 times 10 raised to the -19 divided by the whole Planck constant. 6.626 times 10 raised to the -19. I mean, no, -34, sorry. So, 3.0277186675 divided by 6.626 0.456945166. Dad told me to estimate those to just 2 decimals. But remember, the two decimals is smaller than the real whole value.
That's true.
45166 times 10 raised to the 15.
Very good.
You can use addition to solve subtraction. That's what my teacher at first grade taught me. 456945166 times 10 raised to the 14.
So
This is what I was expecting to get.
Let's see that. We found the frequency, so let's find the wave.
I remember from my room, lambda is hc/E. But we're not using that equation.
Oh, is there a different one you're going to use?
The Rydberg equation. Yeah. Let's just give credit to him. 1 over lambda is equal to R 1 over an initial squared minus 1 over a final squared. Trust me, we're going to get the same thing as if lambda is hc/E.
Oh, that's good. I was kind of worried about that.
9 minus 1 over and final squared, so 4. So 1.0974 times 0.13, a couple of 8. Oh god, I'm spamming the 8 button. 9. So 0.152416666, the beast number. So 0.152416666. You can see the beast number in there.
There it is.
So times 10 raised to the 7. So 1.52416666 times 10 raised to the 6. So that's 1 over lambda. Now if we do cross multiplication, answer times 10. Okay. I think I'm on the right point. So 1 is equal to lambda times 1.5241666 times 10 raised to the 6. Oh, 4 6s, sorry. I didn't want to write the beast number in there. So.
Okay, so now what do you do?
Yeah, so you want to find for lambda.
That's right.
Wait. So.
What's a good way to solve for lambda?
So we can isolate lambda by both sides by this huge value.
Oh, good. Yeah, that'll work.
So lambda is equal to 1 divided by 1.52416666 times 10 raised to the 6.
Uh-huh.
Wow, that's a lot of 6s.
That's a lot of 6s.
So 1 divided by 1.524146. Oh, I put 3 6s. Oh, great.
Well, it's probably close enough.
Yeah. I still got 656. So that's equal to 656 nanometers, I think.
Very good. Okay, so you've got the wavelength.
656 nanometers.
What color is that light?
Give you an example of the hydrogen emission spectrum.
Please do.
This is hydrogen gas. When hidden with pure high energy, it will split into two hydrogen atoms. All of those emit a pale pink light. And when you put that pale pink light through a prism, it splits into 4 colors: violet, blue, turquoise, and red. Red being the one with a wavelength of 656 nanometers.
Oh, you know the wavelengths of the others too?
Yeah. This is turquoise, 46 nanometers. This is blue, for 34 nanometers, and this is violet with only for 11 nanometers. So they range kind of from 400 all the way to 750. At least that's what the diagram says.
Okay, very good.
I think they range from 400 to 700.
Uh-huh. Oh, very good. And I guess one more question. Can you tell me, can you figure out the speed of light from all of this?
Oh. C is lambda times the frequency. 6 nanometers. So if we make it smaller and smaller, so 656 nanometers, 65.6 would mean -8, and 6.56 would be -7.
That's right.
So 4.5 times 6.56.
Mm-hmm.
So this. Wait. 4.5 times 6.56 is 29.52.
Okay.
Which Dad always likes to round to 30. He always rounds decimals to whole numbers.
Is that right? Oh, okay. Well, we'll let him do that.
So 29.52 times 10 raised to the 7, because 14 minus 7 is 7.
Oh, good.
So let's make this in scientific notation. 2.952 times 10 raised to the 8. Hooray! We got the speed of light.
Congratulations. Okay. How about the double slit experiment? Do you want to tell me about the double slit experiment?
Okay.
In the beginning, you said that light is a particle. Is it really a particle?
Einstein with an IQ of 160, he also used the light as a particle so he could explain the photoelectric effect and find the velocity of photoelectrons.
Uh-huh. But suppose you have two beams of light that are crossing each other's paths, then they don't interact at all. And
If they were made out of particles, so these are the two beams of light, right?
mm-hmm.
They were made out of, Newton and Einstein took them as particles.
Uh-huh.
You would say if they were made out of particles, then they would bounce off in random directions.
That's exactly what I'd think.
Yeah, but that did not happen at all.
Okay. So,
They just randomly passed through each other.
okay. Okay, and I guess another problem is that light makes interference patterns. Can you explain to me why light makes an interference pattern but particles don't?
Okay. So, let's see. This is a combination of particles ampersand waves.
Uh-huh.
We can split it into three categories. Marbles, water waves, and electrons.
Uh-huh.
Electrons being the sort of particle we're using because they represent light,
Okay.
as I said in chapter 4. So, marbles, if they go through one slit, they will have one band.
Mm-hmm.
There will be one band appearing on a wall. If they go through two slits, there will be two bands appearing on the wall.
Mm-hmm.
Now let's go with water waves.
Okay.
So, water waves classify so one slit, two slits.
Mm-hmm.
One slit will give you one band just like a marble, but two slits will give you an interference pattern of many bands.
Uh-huh.
Now, let's test the electrons.
Let's do that. How do electrons behave?
Actually, I think this could be a better way to show electrons. So, one slit, two slits.
Mm-hmm.
One slit will give you one band, just as you expected, but two slits will give you an interference pattern of many bands.
Really?
How
Just
could
like a
this
water
happen?
wave?
Yeah, this is similar to the behavior of a water wave.
See. Okay.
The scientists thought they were shooting electrons too fast, so they tried to shoot electrons more slowly.
Uh-huh.
Electrons in slow mode.
Uh-huh.
But after 60 minutes or 1 hour of the same thing, after 60 minutes of two slits and shooting it one at a time,
Mm-hmm.
they still got an interference pattern of many bands.
Really? That's very interesting.
But then scientists became a little clever, and they put an observer next to one of the slits to see which slit electron exactly went through.
Uh-huh.
So electrons with observer.
Mm-hmm. So somebody who's watching which slit it goes through?
Probably a machine observer. After an electron and observer with two slits. With an observer, it went back to behaving like a particle.
Really?
Only two bands.
Huh. That's very surprising. So now I'm all confused. Is it like a particle or a wave?
I don't know. We will discuss it at the end.
Okay, let's come back to that. Would you like to talk about black holes?
Yeah, we can do it on the space around this.
Well, first of all, can you tell me what is a black hole?
Oh, black holes are such a compressed and small region of space-time. They're sorts of dead stars that are minimum 8 times as large as our own sun. Yeah, their gravitational pull of which is strong that nothing, not even light, can escape it.
Wow.
That's why they're probably black and we cannot see them.
I see. Okay. Can you prove that nothing can move faster than light? Can you tell me how much mass an electron has when it has a speed of 4 times 10 to the 7 meters per second?
Okay, and so the velocity is mass of the electron is 9.11 times 10 raised to negative 31. That's pretty small.
That's tiny.
It's 0 followed by 31 zeros and then followed by a 911, resembling the emergency call.
That's true.
This is just the rest mass of the electron though.
Is there a formula for how much mass it has when it's moving?
Yep. C speed, so moving mass is the rest mass over the square root of 1 minus velocity squared over the speed of light in a vacuum squared.
I see. Very good. Okay.
So 9.11 times 10 raised to negative 31 divided by the square root of 1 minus v squared 4 times 10 raised to the 7th squared divided by c squared. And we found out 2.952 times 10 raised to the 8th squared. 0.01% more mass than rest mass.
Okay.
In other words, 9.19 times 10 raised to negative 31. It's sucky, right?
Okay, so
It's really, really small.
pretty tiny increase in the mass.
Yeah.
What if it's going 98% of the speed of light?
Yeah. It will become pretty big. Its mass will become pretty big.
Okay.
I forgot the graph for it though. It'll be 5 times its own rest mass.
Is that right?
Okay, let's see.
Let's see if that's right.
C, V is 0.98 C, and moving mass is missing.
Right, that's what
Rest mass is also rest mass. Yeah, it's weird. So, moving mass is rest mass, so MO over the square root of 1 minus v squared, so 0.98 c squared over c squared. So these cancel out 5 times the rest mass of an electron.
Really? 5 times as much mass.
Yeah.
That's a big increase. Can you calculate the escape velocity from the Earth?
We want to find the escape velocity. For that, we need the radius of the Earth. For that, we need the radius of the Earth. The mass of the Earth, this This is from the reference table of physics. 5.98 times 10 raised to 24th. The government can't be wrong. And
Let's hope.
And the gravitational constant. This is supposed to be big M. 6.67. Sorry, 6.67 times 10 raised to negative 11. Ha! My perfume smells like sour apples. I need to go drink some juice. Wow. That's like my art teacher's computer. How do we find the escape velocity? Well, PE is KE. K is P too. So potential energy is G, a big M, small m over R squared. Kinetic energy is half of V squared. So the small m cancels. So dm over r. If we multiply both sides, we will get 2dm over r.
Very good.
This 2 came on the top. That's why the r shouldn't be 2r. Don't make that mistake.
I'll try not to.
Equals v squared. So that's the equation we're using. 2dm over r is v squared. That would mean the square root of 2dm over r is v.
Excellent.
So v squared is 2 times 6.67 times the mass of the Earth times 10 raised to the 13, since 24 minus 11 is 13. And we divide that by the radius of the Earth. So 6.4 times 10 raised to the 6. This thing works pretty well.
Oh, good. I'm glad to hear that.
2 times 6.67 times 5.98. That's 9.7732. That's what the calculator gave me.
Okay.
I guess I just know how to operate this calculator very well.
Clearly you do.
Casio. So, over 6.4 times 10 raised to 6. That thing is relaxing, I guess. So, if we divide our answer by 6.4, I never knew this would come up whenever you press enter. So, 12.4645625. 12.4645625 times 10 raised to the 7. So 1.24645 times 10 raised to the 8. If we divide this answer by 10, if we square root 1.24645,625, $1.116448051. So we're good. 1.116448051. Bruh, that's such a small change. How is that the square root?
Let's see. Is there a?
It's a 0.13 change.
I guess that's true. What about the? Is that in scientific notation?
Times 10 raised to the 8. I mean the 4 because of the square root.
There you go.
So that is the escape velocity of the Earth. I'm pretty sure that's the velocity most rockets go to.
I guess that's how fast you need to go if you want to escape from the Earth.
So it's about 11,000. So 11,164.4805 meters per second.
Can you turn the Earth into a black hole?
If you squash it so small that it eventually turns into a black hole. I don't know. We'll have to invent a machine for that. Everything has something called the Schwarzschild Radius. I'm pretty sure the Earth's Schwarzschild Radius is as small as a peanut. That's not how you draw a peanut. Please don't.
Pretty close. That looked like a good peanut to me. You know, for the Schwarzschild Radius.
Oh, yeah. The radius is 2 over r, right?
That's right.
So r must be 2 over v squared.
And to get the Schwarzschild Radius, what do you put in for the velocity?
The escape velocity for black holes are the speed of light. So we're just going to replace v with c.
Oh, very good. Okay, that makes sense.
So 2 times 6.67 times the. So we're going to swap Earth for an equally massive black hole. So times 5.98, not 6 actually. 5.98 times 10 raised to the 24 minus 11 is 13. So the top is basically the same, but the bottom isn't. So 3 times, actually 2.952 times 10 raised to the 8 squared.
Oh, very good. So that's the Schwarzschild Radius for the black hole.
Okay, yeah. So 2 times 6.6. I don't know how the calculator is typing in random things in it by itself. Last time I cleared the calculator, I saw 153.
Okay, I don't know.
Wait, K-A-T-Z?
Yeah, I guess that's a lot of books.
It says K-A-T-Z on both of those physics books.
I guess that's who wrote them.
And Miss Katz is the name of my teacher.
Oh, is that right?
Yeah.
Oh, maybe she wrote the books.
What? She's only a first grade teacher.
Well, you never know.
Okay. But she only taught second grade and first grade.
Okay. Well, yeah, maybe it's somebody else that has the same name. I don't know.
Okay, so 2 times 6.67. Oh God, it typed another thing by itself.
Do you need to clear it again? I don't know.
2 times 6.67 times 5.98. It's like a race between me and the mushroom. So 79.7732.
Okay.
79.7732. So 79.7732. Yeah. Oh God, I just repeated that without knowing. 10 raised to the 13 over 2.952. Wait, is there any square button here?
Oh, there is. Do you see it? It's right there.
Oh, great. 8.714304. 8.714304. This calculator works pretty well.
That's good. Is is there an exponent that goes with that?
Is there 16, 10 raised to the 16. So 79.7732, divide that by 8.714304. You bet it's a decimal, but you never know. It could be a whole number.
Could be.
Okay, I guess it's a decimal. 9.15428243. A very small decimal though. 9.15428243 times 10 raised to the negative 3.
Uh-huh.
Yeah.
So that would be the Schwarzschild Radius for the Earth?
Yeah. That's pretty small, right?
That is about the size of a peanut.
Or maybe it could be bigger than a peanut. Maybe it's the size of a beach ball.
I think it's maybe the size of a big peanut.
Okay.
So if the Earth turned into a black hole, would we be able to survive?
Let's check that out. First, let me.
Why isn't it a good idea? What would happen to us if the Earth turned into a black hole?
Strong gravitational pressure, spaghettification.
We'd spaghettify? Oh no!
Okay. I guess a black hole do have a mouth. They eat spaghetti. So let's make a table between Earth, its force of gravitation, and a equally massive black hole. And its gravitational rotation. I mean, its gravitational force. So I'll draw a wooden test dummy over here. And the wooden test dummy, he's not that heavy. Let's say he does 5 kilograms. His eyes and his. Okay, so this little weirdo is 5 kilograms. So the force of gravitation is Gmm over r squared, right? So 6.67 times 5.98 times 5 times 10 raised to the 13.
Okay.
So we divide that by the radius squared. So 6.4 times 10 raised to the 6 squared. So I'm pretty sure all of this is 80.04. Let me check. 1 times 5.98 times 5. 199.433. So basically 200, but yeah. 199.433. When I entered 6 on my instead of 5.98, that ordered me to draw 6. And I got this different answer.
The force of gravity on this on that weird thing?
Wait. Yeah.
Okay.
I don't. We don't know if he's gonna survive or not. So I mean, what's a 199.433 divided by 40.96? 4.868969727. So I mean, it's close to 5 newtons.
Oh, okay.
So, wait, 13 over 16? No, 13 over 12.
There you go.
So 48.68969 727.
Very good.
So the force of gravitation on that thing is just 10 times its mass. Just a little bit, yeah.
Okay.
But that's nothing compared to the force of gravitation on a black hole.
What's the force of gravity if it's near a black hole?
Yeah, the radius of a black hole is pretty small. So that's why the top would be pretty big. And that means it's a whole lot bigger.
Okay. Can you figure out what the force would be?
Yeah, so the top would be the same, so 199.433 times 10 to the 13 over 6.4 times 10 to 8 times 10 to the negative third squared. So 8 squared is 64. Actually, it was around 9, I think. So 9 times 10 to the negative 3, 9 squared is 81. So 81 times 10 raised to the negative 6. 199.433 divided by 81 is 2, but times 10 to the 19. So 2.462 times 10 to the 19.
Wow.
That's a whole lot more newtons.
That's a huge force.
Yeah, so the test dummy would get ripped and shattered.
Oh, okay.
Oh wait, shattered is not the right word because this test dummy is only made out of wood, no glass.
Well, he'd get smushed, that's for sure.
Yeah.
Wow, okay.
Must like you squish Play-Doh with your hands.
Okay.
Yeah, so we wouldn't survive on a black hole. We'd have the same effects.
Yeah, it would smush us too. Alright, so...
Black holes don't exactly squish us, just spaghettification. Neutron stars squish us. Man, I can't really say neutron stars correctly.
You did a good job. So let me come back to the question that we talked about at the beginning. What is light?
I don't know, Dr. Kabat. Sometimes it acts as a wave, and sometimes it acts as a particle.
So is it a wave or is it a particle?
I don't know. It has a wave-particle duality. And that's all I can say.
That's all that anyone can say. Wow, good job, Isaac. This was very impressive.
Yeah.
Excellent job. Congratulations.
Isaac Bari, known as God of Mathematics. Subscribe to Bari Science Lab to fall in love with math and science.